Bismillahirrahmanirrahim. So now we are going to proceed with another lecture related with the X-ray spectroscopy. So X-ray spectroscopy is based on the measurement of that emission, absorption, scattering, fluorescence and diffraction. यानी कि हमने जो अभी पिछले लेक्चर्स में हमने कवर की बात तो वो ये थी कि एक्स-रे जब किसी मैटर के साथ इंटरेक्ट करते हैं तो वो डिफरेंट फिनोमेना के थ्रू जो वो प्रोसीड करते हैं. बट एक्स-रे स्पेक्ट्रोस्कोपी इटसेल्फ कौन कौन से जो उस पे प्रिंसिपल पे बेस करती है. वन इज द एमिशन, absorption, scattering, fluorescence and diffraction of electromagnetic radiations. So for analytical purposes x-rays are generated in 4 ways. अब यहाँ पे देखें x-rays की जनरेशन की बात हो रही है. पहले क्या था, हम x-ray की जनरेशन की बात नहीं की. पहले हमने ये कहा कि x-rays की किसे भी जनरेट हुए, किसी भी सोर्स से जनरेट हुए, लेकिन एक्सरेज जब मैटर के साथ इंटरेक्ट करेंगे तो कौन से फिनोमेना को फॉलो करेंगे. लेकिन अभी हम ये पढ़ रहे हैं कि एक्सरेज खुद जनरेट कौन कौन से तरीकों से हो सकते हैं. सो नंबर 1 इज बाय बम्बार्डमेंट ऑफ मेटल टारगेट विद द बीम ऑफ हाई एनर्जी इलेक्ट्रॉन. किसी भी मेटल टारगेट को जो है वो हाई एनर्जी बीम से अगर बम्बार्ड करवाया जाए तो एक्सरे की प्रोडक्शन होती है. नंबर 2 बाय एक्सपोजर ऑफ अ प्राइमरी सब्सटेंस टू अ प्राइमरी एक्सरे बीम, यानी जो सब्सटेंस है जहां जिस सब्सटेंस से हमने एक्सरेज इजेक्ट आउट करवाने हैं या एक्सरेज प्रोड्यूस करवाने हैं उस सब्सटेंस को बजाय हाई इलेक्ट्रॉनिक बीम्स के हम पहले ही जो है वो एक प्राइमरी बीम ऑफ एक्सरेज से हम जो है वो बम्बार्डमेंट कराएं और सेकेंडरी बीम ऑफ एक्सरेज जो है वो जनरेट हो, जिसको कि एक्सरे फ्लोरेसेंस कहा जाता है. थर्ड वन इज दी बाय द यूज ऑफ रेडियो एक्टिव सोर्स whose decay process results in the X-ray emission. कोई भी हम रेडियोएक्टिव सोर्स यूज करें जो जब डिके हो, जब ब्रेक डाउन हो और उसके रिजल्ट में जो है वो एक्स-रेज प्रोड्यूस हो. Number 4 is from the synchrotron radiation source. Only a few laboratories in the US have facilities to produce X-ray from synchrotron radiations. These are also the radiations which are synchronized in nature और उनको जो है वो किसी भी मेटल टारगेट पे बम्बार्ड करके एक्स-रेज की प्रोडक्शन करवाई जाती है. तो जनरली 3 तरीके से. 1 के मेटल टारगेट को किसी भी हाई इलेक्ट्रॉनिक बीम से बम्बार्ड करवाया जाए. 2 मेटल टारगेट को किसी भी प्राइमरी एक्सरे बीम से इंस्टेड ऑफ हाई इलेक्ट्रॉनिक बीम प्राइमरी एक्सरे बीम से जो है वो बम्बार्ड करवाया जाए और उसके रिजल्ट में एक्सरे फ्लोरेसेंस जो है वो कहलाती है. और थर्ड वन फ्रॉम द रेडियो एक्टिव सोर्स जिसके डीके प्रोसेस से एक्सरेज जनरेट होते हैं. सो एक्सरेज often produce both. जब एक्स-रेज जो है वो निकलते हैं तो वो 2 तरह के स्पेक्ट्रॉस देते हैं. वन इज द कंटिन्यूम जिसको के ब्रेमस्ट्रोलॉन्ग कहा जाता है एंड अदर वन इज द लाइन स्पेक्ट्रा जिसको के कैरेक्टरिस्टिक्स कहा जाता है. सो इस तरह के 2 स्पेक्ट्रम जनरेट होते हैं. एक्स-रे किसी भी सोर्स से प्रोड्यूस हो लेकिन वो 2 तरह के स्पेक्ट्रम देता है. वन इज द कंटिन्यूअस व्हिच इज also called as a bremsstrahlung. Another one is the line spectra, also called as characteristics. Both types are of importance in analysis. Continuum radiations यानी जो के bremsstrahlung है उनको white radiation भी कहा जाता है. Whereas bremsstrahlung की term जो bremsstrahlung है उसकी meaning क्या है? Arises from the retardation of particles यानी के breakage. Bremsstrahlung means breakage, retardation, रुकावट, किसी भी particle के अंदर रुकावट लाना. Such a radiation is generally the spectral continuum. Here is a video representation through which you can easily understand about what are the bremsstrahlung interactions. ठीक है, इस तरह से आप जो है वो इस वीडियो की हेल्प से easily understand कर सकते हैं.
X-ray tubes produce X-ray photons by sending high-speed electrons from the cathode to the anode. As the electrons hit the anode, their kinetic energy is converted to X-ray energy. The most common type of electron-anode interaction is the Bremsstrahlung interaction. Bremsstrahlung is the German word for breaking or slowing radiation. It may also be referred to as Brem's radiation, and it is produced when projectile electrons are slowed down in the anode. Due to the electrostatic attraction between the electron and the nucleus, The electron is deviated from its straight line path. As it turns, it decelerates or slows down. This change in kinetic energy results in an X-ray photon being produced equal in energy to the amount of kinetic energy lost. This satisfies the law of conservation of energy. Bremsstrahlung interactions are responsible for producing a wide variety of X-ray photon energies. Because electrons may approach the nuclear field at different angles and speeds, different energy levels of photons will result. When an electron is not decelerated to as great a degree due to a less sharp turn, a lower energy photon is produced. Note the lower frequency and longer wavelength of this Bremsstrahlung photon. In the case of this electron, it has been deviated greatly from its original path, causing it to slow down even further. Because this electron has experienced the greatest change in its kinetic energy than the previous two electrons, it produces a photon with even greater energy than before, as seen by its increased frequency and decreased wavelength. 90% of the X-rays produced in the X-ray tube are due to Bremsstrahlung interactions. Because of the wide variety of energies produced as a result of this process, Brems radiation is responsible for the heterogeneous nature of the X-ray beam.
Yes, so it was about the Bremsstrahlung interactions. आपने देखा कि Bremsstrahlung interaction is basically the deviation, depends on the deviation. कि क्योंकि अगर देखें आप यहाँ पे क्या था, इलेक्ट्रॉन की बम्बार्डमेंट हो रही थी, 90 किलो इलेक्ट्रॉन वोल्ट की बम्बार्डमेंट हो रही थी, और वो जिस एंगल से जितना डेविएट हो रहा था उतनी वो एनर्जी लूज करके बाकी एनर्जी के जो है वो एक्सरे फोटॉन्स रिलीज कर रहा था. तो ये इस तरह के फिनोमेना को कहा जाता है ब्रेम्सट्रॉलॉन. ठीक है, देयर इज अनदर रिप्रेजेंटेशन यू कैन सी.
Hey everybody, welcome back. This video is an overview of Bremsstrahlung radiation, one of the target interactions that creates X-ray photons in the X-ray tube. First, let's remember there are three essential requirements for creating X-ray photons. First, a source of free electrons. Secondly, a means of accelerating those electrons. And thirdly, a process for deceleration of those electrons. Each of these steps is controlled by different components and processes inside of the X-ray tube. Free electrons are created at the cathode filament through the process of thermionic emission. These electrons are accelerated through the X-ray tube by a voltage, that's the kVp. These electrons are decelerated when they interact with the tungsten atoms in the anode target, and through that process, they create X-rays. Bremsstrahlung radiation is one of the processes through which these X-ray photons are created. So here's how it works. A tungsten atom, like all atoms, has a positively charged nucleus because of the protons, and it's surrounded by negatively charged electrons. All of these charged particles have an electric field that radiates around them. The nucleus has a positive electric field, and the electrons have a negative electric field. When electrons from the cathode enter the anode, some electrons are attracted to the positive charge of the nucleus within these tungsten atoms. And that makes sense. The negatively charged electron is attracted to that positive charge in the nucleus. But when this happens, the electrons slow down or break, and they also change direction, called deflection. This lost energy is released in the form of an X-ray photon. This process has a name. It's actually called Bremsstrahlung radiation. Bremsstrahlung is the German word that means breaking radiation. And that makes sense because the radiation is created because the electrons break or slow down. So you can kind of think of it like this. If you throw a ball at a glass window, the ball will slow down and usually get deflected another direction, just like when the electrons pass near the tungsten nucleus. But what happened to all of the energy that the ball was carrying? It had to go somewhere. The law of conservation of energy says that energy cannot be created or destroyed. It can only change in form. So some of that original energy is left in the ball, but some of it leaves the ball and creates cracks in the glass. And this is just like how some of the electron energy leaves the electron and creates an X-ray photon. The energy of a Bremsstrahlung radiation photon depends on a few factors, one of them being the energy of the incoming electron. If the incoming electron has an energy of 100 keV, the maximum energy photon that can be created is 100 keV. They won't always have the maximum energy, but they can. Here's another example. If the incoming electron has an energy of 75 keV, the absolute highest energy photon that we can get out of that electron would be 75 keV. The maximum energy of a Bremsstrahlung X-ray photon is controlled by the kVp. So the tube potential, if it's set to 100 kVp, will create Bremsstrahlung photons that have a maximum energy of 100 keV. And of course, if we change the kVp, this changes. If the tube potential is set to a kVp of 75, the maximum Bremsstrahlung X-ray photons will have an energy of 75 keV. Not many Bremsstrahlung photons are going to have this maximum energy. And why is that? The energy of Bremsstrahlung radiation also depends on how close the electron passes to the nucleus. If the electron passes very close, as in this example, it will slow down significantly, change directions completely, and give up most of its energy as an X-ray photon. For example, if the electron approaches with an energy of 90 keV, it'll slow down to almost zero and release a photon with an energy of about 90 keV. But these electrons don't always pass very close to the nucleus. Here's another example. Let's say in this scenario, the electron passes at a much greater distance from the nucleus, and things will change. The attraction between the electron and the nucleus is weaker. The electron slows down some, but not completely. It changes direction some, but not completely. And it only gives up some of its original energy. For example, if the electron approached the atom with an energy of 90 keV, but slowed down to an energy of 60 keV, the resulting photon would have an energy of 90 keV minus 60 keV, which is 30 keV. All of the energy here is accounted for. It might be helpful to look at a graph of X-rays created during a single X-ray exposure. The x-axis is the different photon energies in the X-ray beam. The y-axis is the number of photons with that energy. So the tallest part of the curve represent the photon energies that appear most often in the X-ray beam, and it's right in the middle. This large bell curve represents the Bremsstrahlung X-rays. A single exposure creates hundreds of millions of X-ray photons, and almost all of these are Bremsstrahlung X-rays. The curve is short on the left because very few Bremsstrahlung X-rays have such low energy. This would come from electrons that slow down not much at all. The curve is also very short on the right, and that's because very few Bremsstrahlung X-rays are created with the highest possible energy. These photons would come from those electrons that slow down to nearly zero and release all of their energy as a photon. The curve is tallest in the center because most Bremsstrahlung X-rays have a moderate energy level, above zero, but less than the maximum energy set by the kVp. So what's that large spike on the right? That is characteristic radiation, which is the topic of the next lesson. Hey everybody, welcome back. This video is Hey everybody, welcome back.
So this was all about the Bremsstrahlung interaction. So now there is a turn for the characteristic X-ray effect. Now you see Bremsstrahlung के अंदर क्या था कि रेडिएशन हो रही थी, जो है वो इनकमिंग जो इलेक्ट्रॉन था वो आके न्यूक्लियस और जो है वो सराउंडिंग इलेक्ट्रॉन्स की इलेक्ट्रिक न्यूक्लियर फील्ड जो है वो इफेक्ट की वजह से जो है वो डेविएशन हो रही थी. जितनी ज्यादा डेविएशन हो रही थी उतनी ज्यादा वो एनर्जी लूज कर रहा था और वो रिजल्टिंग उतनी ज्यादा जो है वो एनर्जी का एक्सरे रिलीज हो रहा था. लेकिन जो है वो टोटल एनर्जी अकॉर्डिंग टू द लॉ ऑफ कंजर्वेशन ऑफ एनर्जी द टोटल अमाउंट ऑफ एनर्जी रिमेन्ड सेम. लेकिन कैरेक्टरिस्टिक एक्सरे इफेक्ट के अंदर द फिनोमेना इज अ लिटिल बिट डिफरेंट. इसके अंदर क्या होता है कि एक जो इनकमिंग फोटोन है वो आके जो है वो द इनर मोस्ट इलेक्ट्रॉन को इजेक्ट आउट करता है और वहां पे एक वैकेंसी क्रिएट कर लेता है। जो वैकेंसी जो है वो नियर बाय शेल के इलेक्ट्रॉन से आके फिल हो जाती है और एज अ रिजल्ट जो नियर बाय शेल ऊपर से जब नीचे आया तो उसने एनर्जी
In this video tutorial, I will
that
teach you about
energy
the
is in
characteristics
the form of the X-rays. Now you can learn with the help of this video again. ये एनर्जी जो रिलीज हो रही है that is due to the
In this video tutorial, I will teach you about the characteristics X-ray effect in detail. So, in characteristics X-ray, how it will be take place, I will be teach you. So, here this blue one represent my atom. For this atom is made up of tungsten, and in the center of it is purple one represents the nucleus. The nucleus consists of neutron and proton, and outside of the this purple one is located shells, or you can say orbital electron, which consist of k shell, l shell and m shell. Each shell consists of their own electron. As you see, k shell consists of 2 electron, l shell consists of 8 electron, and so on. So in this characteristic X-ray, what happens is that this my is a electron. Whenever electron come with high speed, then it will be strike with the any of the orbital electron. When it strike with the orbital electron, then it will be ejected out the k shell electron, plus it will be deviate from its original direction. After electron will be ejected out, now the atom is unstable. Now here a vacancy is created. Now to make a atom stable, the upper shell electron will be now fall in this lower shell vacancy which is created here. Now you see that the electron which is located in the L shell will be fall here in K shell to make it stable. Now after the electron from the L shell will fall into the K shell. By doing this the X-ray is emitted. Now this type of energy emitted is known as characteristic X-ray, because it is a particular characteristics of that X-ray. For in this example, the K shell of target having binding energy of 69.5 keV, whereas L shell having binding energy of 10.2 keV. So when the electron from L shell to fall into K shell, then the energy emitted is 59.3 keV. You will be say here. So if the electron from M shell to fall in the K shell, then energy emitted is 69 keV. So on.
So this was about the characteristic interactions. I hope you understand very well. कि इसके अंदर क्या होता है कि एक जो है वो वैकेंसी जनरेट होती है, इनर मोस्ट इलेक्ट्रॉन से इलेक्ट्रॉन रिजेक्ट आउट हो जाता है, जो कि वैकेंसी नियर बाय शेल से इलेक्ट्रॉन आके फिल करता है. एज अ रिजल्ट जो एनर्जी डिफरेंस होता है एल और के के दरमियान, वो सेपरेट होके और बाकी एनर्जी के डिफरेंस से जो है वो एक्स रेज रिलीज आउट हो जाते हैं. ठीक है, तो ये कहलाता है कैरेक्टरिस्टिक एक्सरेज. जबकि पहले था ब्रम्स्ट्रॉलोंग इंटरैक्शंस जिसके अंदर डेविएशन थी. ठीक है, और कैरेक्टरिस्टिक के अंदर वैकेंसी क्रिएट होती है और वैकेंसी क्रिएट जो है वो क्रिएटेड वैकेंसी फिल्ड बाय द नियर बाय शेल्स इलेक्ट्रॉन. एज अ रिजल्ट द एनर्जी इज रिलीज्ड व्हिच इज कॉल्ड एज द एक्स-रेज. So there is another representation you can easily learn with the help.
X-ray tubes produce X-ray photons by sending high-speed electrons from the cathode to the anode. As the electrons hit a tungsten anode, their kinetic energy is converted to X-ray energy. Two processes are responsible for producing X-ray photons: Bremsstrahlung and characteristic. While Bremsstrahlung is responsible for producing the majority of X-ray photons, once an electron's kinetic energy reaches 69.5 keV and above, characteristic interactions will begin occurring. This is because a tungsten atom's K-shell binding energy is equal to 69.5 keV. A characteristic interaction occurs when a 69.5 keV electron approaches an atom and ejects a K-shell electron from its orbit. In this case, a 70 keV electron is shown ionizing the tungsten atom. This ionization event creates a vacancy in the K-shell of the atom. Because the atom is now electrically charged due to a missing electron, it works to restore its neutral charge by filling the vacancy with an electron from an outer shell, usually the L shell. The atom continues to neutralize itself by having an electron from the M shell fill the vacancy left in the L shell. In turn, an N shell electron serves to fill the vacancy in the M shell.